Hello friends, I Professor Darshan Thakur welcomes you on my YouTube channel for this subject here digital communication. As far as our today's session is concerned, so we will try to learn this the most important digital modulation scheme of this passband transmission system, whose name is nothing but binary phase shift K. Right. So first question arises in our mind K, what this K stands for, right? Now, according to the definition of this modulation, K'ing is nothing but what? The way in which we are changing the basic parameter of this unmodulated carrier signal, which is nothing but either amplitude, phase or frequency, because these three are the important performance parameter of this carrier signal or sinusoidal signal, or we can call it as a high frequency signal, right? So this BPSK falls under the category of a digital modulation scheme because due to the nature of its modulating symbol sequence, because as far as the modulation is concerned, so in case of modulation always there will be an involvement of two different test signal. Out of that two test signal, one is nothing but what, for sake of this moment, this square waveform or this NRZ symbol sequence can be called it as a modulating symbol sequence, and this sinusoidal signal can be called it as a carrier signal. So always there will be involvement of modulating and carrier. So if the nature of this modulating signal is in digital form, so obviously this BPSK falls under the category of digital modulation scheme, or in either way we can call it as a continuous wave digital modulation scheme, because the nature of this carrier signal is a continuous signal. That's why it is being called it as a continuous wave digital modulation scheme. Now the question arises as far as this BPSK is concerned. So in case of this binary phase shift keying, as its name indicate, we are supposed to change the phase of this unmodulated carrier signal, or we are going to modulate this unmodulated carrier signal with respect to this digital modulation symbol sequence, in which what exactly we are doing, as far as this signal presentation is concerned, or this fourth waveform is concerned, basically there are four different of signal representation as far as these waveforms are concerned belongs to this BPSK. One by one we will try to discuss. First one is nothing but what, the desired binary symbol sequence which is being given to one of the input of this BPSK modulator. The second symbol sequence is nothing but what, it is the NRZ biopolar symbol sequence, which consists of two polarities, belongs to binary 1 and belongs to binary 0. Plus 1 volt is for binary 1 and minus 1 volt is for binary 0. Third one is nothing but what, this is the desired carrier signal which is being given to one of the input of this BPSK modulator. Now how this BPSK modulator works, laterly we will try to discuss. So as I told you earlier, in case of this modulation, always there will be involvement of this modulating and carrier signal, right? So in case of this binary phase shift keying, here what exactly we are doing, as I told you earlier, whenever, see, this is the digital binary symbol sequence belongs to modulating signal, which consists of 1, 0 and 1. So this is nothing but what, the bit duration for 1 as well as 0 for 1. Which is mentioned in terms of few seconds, right? So in case of this binary phase shift keying, the modulating symbol sequence consists of two different symbols, 0 and 1, right? So obviously the total time period for sinusoidal signal is what, 360 divided by 2. So how much it is? 180 degree, right? So by an amount of 180 degree, whenever we are going through the signal transition, at that time the unmodulated carrier signal or the phase of this unmodulated carrier signal is being changed by an amount of 180 degree. This is the basic of this binary phase shift keying. As I told you earlier, this modulation involves the modulating signal and the unmodulated carrier signal. Here in case of BPSK, we are dealing with which parameter of this unmodulated carrier signal? We are dealing with the phase of this carrier signal, right? So as you can see, whenever we are transmitting the first binary bit, that is nothing but what, 1. So while transmitting this binary 1, all the amplitude levels of these carrier signals are being passed as it is, right? But when the signal changes from 1 to 0, as far as this NRZ, or we can call it as a not return to 0 bipolar symbol sequence, when we are going through the signal transition from 1 to 0, right? So carefully you just try to see, in case of this BPSK signal envelope, the phase of this unmodulated carrier signal is being changed by an amount of 180 degree below this horizontal reference line whenever we are going through the signal transition of 1 to 0. Obviously, whenever we are going through the signal transition of 0 to 1, at that time also the phase of this unmodulated carrier signal is being changed by an amount of 180 degree above this horizontal reference axis. So by an amount of 180 degree each time whenever we are going through the signal transition, the phase of this unmodulated carrier signal is being changed by this BPSK modulator, right? So this is the basic of this binary phase shift keying, right? Now let us quickly go through the BPSK generator. As you can see, the BPSK generator, which consists of two identical blocks. First of all, we need to understand what type of input is being given to this BPSK generator. So the input is nothing but what? The first signal representation, the desired binary symbol sequence, which is being given to this bipolar NRZ encoder. So basically, NRZ encoder, what it will try to do, it will accept the unipolar symbol sequence and it will generate the bipolar or not return to 0 binary symbol sequence, which consists of two different polarities for 1 as well as 0, right? Then the second block is nothing but what? The balanced modulator, right? As far as this balanced modulator is concerned, so to that balanced modulator, there are two identical inputs, those are being given. First is nothing but what? The NRZ type of binary symbol sequence, and the second input of this balanced modulator is nothing but what? C of t, the unmodulated carrier signal, right? So basically modulator will try to multiply these two symbol sequence, modulating symbol sequence and the carrier symbol. Means ultimately it will try to suppress the desired carrier signal and it will generate the BPSK envelope, in which, as I told you earlier, each time whenever we are going through the signal transition from 0 to 1 or 1 to 0, we are changing the phase of this unmodulated carrier signal by an amount of 180 degree, right? Now, in order to understand the generation of this BPSK envelope, first of all, we need to understand how to represent these two symbol sequence in case of modulating signal, as we are having binary 1 and binary 0, right? Now as far as the second input is concerned of this balanced modulator, so what it is nothing but what? The desired carrier signal. Carrier signal means it is nothing but what? The sinusoidal signal. So first of all, we need to understand the generalized mathematical representation of this sinusoidal signal, right? So this is how this sinusoidal signal is being represented mathematically, denoted by S of t equals to what? A into cos of 2 pi f naught t, right? Where this A is nothing but what? The peak amplitude of this unmodulated carrier signal, right? So this is how mathematically this carrier signal is to be represented, right? Then after that, another important aspect of this carrier signal is concerned, we are very much aware of this thing ki the total power dissipation through this carrier signal is denoted by this expression P equals to what? A square by 2. So we can rewrite this statement in terms of this amplitude. So obviously A equals to what? Root 2 times of P, right? So when we substitute this desired amplitude into this expression, if suppose we can call it as the expression number 1, which is nothing but the generalized representation of this carrier signal. So it will become what? This S of t equals to B of t into root 2 times of P into cos of 2 pi f naught t, right? Where what this B of t stands for? This B of t is nothing but what? Whether we are transmitting the binary 1 or binary 0. When we are transmitting binary 1, so obviously how to represent this carrier signal? That can be called it as a S1 of t, right? So where this B of t is being replaced with this binary 1 when we are transmitting 1. So it will become root 2 times of p into cos of 2 pi f naught t, right? And how to represent binary 0? Now, as I told you earlier, in case of whenever we are going through the signal transition from 0 to 1 or from 1 to 0, by an amount of 180 degree, we are supposed to change the phase of this unmodulated carrier signal. So mathematically, how to represent? So with the help of this statement, it will become what? Root 2 times of p into cos of 2 pi f naught t plus pi, where pi stands for what? The desired degree by which we are changing the phase of this unmodulated carrier signal, right? So obviously, as we know, cos of theta plus pi equals to what? Cos of minus cos of theta. Cos of theta plus pi equals to minus cos of theta, right? So here root 2 times of p into cos of 2 pi f naught t plus pi equals to what? Obviously, it will become, how to represent this zeroth symbol in case of binary phase shift keying signal technique? Minus root 2 times of p into cos of 2 pi f naught t, right? So this is how these two symbols are being represented by taking into account the basic expression for this carrier signal, right? So this is how we are generating, or what this statement stands for, if we are marking this statement as a equation number 2. So this equation number 2 is nothing but what? The way in which we are generating the envelope of this BPSK signal, which consists of B of t is nothing but what? The binary symbol sequence, which consists of either 1 or either 0. If it is 1, it is to be denoted with this symbol. If it is 0, then it is to be denoted with this symbol. So this is how the desired BPSK signal is being generated. Now in that remaining part, we will try to learn the receiver section of this BPSK signaling technique, or the BPSK modulation technique.